Hello. In this video, we will discuss about the Kelvin model. First, we will start by deriving the stress strain relations for the Kelvin model, and we will also show through examples how to find the response for a given load. So, as we discussed in previous lectures, saying that Kelvin model is when we have one spring and one damper both in parallel to each other. The spring is represented by this modulus E and the damper with the viscosity mu. So, we will first look at the stress strain relations or derive the stress strain relations, and then we will see what is the response when we apply a creep load for this Kelvin model. Later, we will again come back to superposition and see how we can use it to apply or find response to loads which are not simply like creep or relaxation, but we will look two cases, one creep recovery and second as the realistic creep loads. So, we will get to each of these in more detail from. So, first let us look at the Kelvin model. Here we are trying to derive the relation between the stress and strain, where we have the one spring parallel to the other damper as shown here. So, given here are the stress strain relations for each of these elements. For the spring, we give the stresses in the spring sigma s is E times the stresses in strain in the spring epsilon s, and for the damper stress in damper sigma d is simply the viscosity times the strain rate in the damper. Same with the Maxwell model, we first by writing the equilibrium equations and the kinematic equations. So, first let us start with the equilibrium equation. So, looking at the spring and the damper in parallel, we can say the applied stress will be shared between the spring and the damper, and the total stress is sum of the stresses in the spring plus stresses in the damper. Now, coming to the kinematic equation. So, since both are again in parallel, the strain, the overall strain is the same in the spring as well as the damper. So, epsilon is equal to epsilon s is equal to epsilon d in the damper. Okay. So, again let us name these as equations 1, 2, 3 and 4. So, let us start from equation. So, let us start from equation 3. So, which is written as sigma equals sigma s plus sigma d, but from equations 1 we know that sigma s can be replaced as E times epsilon s, and the second term sigma d can be replaced with equation 2 as mu times epsilon d dot. Now, from equation 4 we can replace all these strains with a overall strain epsilon. Sigma is equal to E epsilon plus mu epsilon dot, and this also is in the standard form. So, we can take this as the final expression for relations of stress and strain, because we have all the stresses to the left hand side and the strains to the right hand side. So, this is an easy derivation, because in two steps we are able to show the relation between the stress and strain. But now let us use this stress strain relation to show what is the creep response for a Kelvin model. So, for Kelvin model, we derived the equation as for a creep load, we know it can be written as sigma equals sigma naught times h of t. So, let us substitute equation 2 into 1. That should give us sigma naught into h of t equals E epsilon plus mu epsilon dot. Now, let us take the Laplace on both hand sides. Now, let us take the Laplace on both sides. It should give epsilon naught times 1 by s equals E epsilon of s plus, now we have the first derivative of the function, like we have been doing it previously, we will write it as s times epsilon of s. We are ignoring the second term because to the left of time t equal to 0, there is no input nor response. Okay. Now, let us simplify this equation by bringing to the left hand side the response epsilon of s. This is written as sigma naught times s times E plus mu s. So, again let us simplify this so that we can write it in a standard terms of where we can have 1 by s plus some constant times s plus constant a. So, for this first let us bring the denominator into s plus constant. For that we will multiply both sides, both numerator and denominator by with 1 by mu. So, sigma naught by mu should give us s times s plus E by mu. Okay. But to further simplify this, we said we have this sigma naught by mu in the denominator, in the numerator, and in the denominator we have this s times s plus E by mu. So, let us try to get this E by mu in the numerator, then we can add in subtract as like what we have done for the Maxwell models. So, how do we get E by mu here? We again multiply with mu by E. So, these mu and mu cancel out each other, and now I can add and subtract s. Once it is in this format, it will be easy for me to write because it will be sigma naught by E times the first two terms is in the denominator. So, it will be simply 1 by s minus 1 by s plus 1 by tau. So, again I will replace it with the relaxation time. E by mu is nothing but 1 by relaxation time. Now, let us we are ready to apply the inverse Laplace transform, and once we applied that, we get to the left hand side is strain in the time domain is given as sigma naught by E times inverse Laplace transform of 1 by s we have seen is nothing but constant 1 minus this inverse Laplace transform of 1 by a can be written as e power minus t by tau. This should give us the creep response of a Kelvin model. Again, like previous cases, so let us visualize it so that we can appreciate what this equation is showing us. So, first let us look at the input to start with. With time, since it is creep, the stress is applied as sigma naught, and now we are looking at what is the strain response. So, with time we want to know how the strain varies. So, to visualize the response, first again plug it, let us look at the instantaneous response at time t equal to 0. Once you plug in time t equal to 0 in the equation, we should get it as sigma naught by E times 1 minus e power 0 is 1. So, overall it should be 0. And what happens at time tending to infinity? Time tending to infinity, the strain is epsilon naught by E times 1 minus e power minus infinity by tau, which will go to 0. So, since this term goes to 0, it will reach a constant value of sigma naught by E. So, we said that it starts with the origin at time t equal to 0, and after it increases it reaches a constant value. And this constant value is sigma naught by E. But now also let us look at what happens at relaxation time tau. So, when we replace time t equal to the relaxation time tau, the corresponding strain is epsilon naught by E 1 minus e power minus 1, because tau by tau is 1 and e power minus 1, which is simply sigma naught by E into 1 minus 1 by E. So, we know that 1 by E, we have previously shown it to be 36.8%. So, which means we know that this saturation value, let us pick a different color, this saturation value or the long term value we said is epsilon naught by E. If you reduce it by 36.8%, it should be somewhere here. So, what we are saying it is this value is our 36.8%, which corresponds to 1 by E. So, the corresponding time is nothing but the relaxation time tau. So, this 36.8% is strain at infinite time by E, and what is left out is this 63.2%, which is epsilon infinity times 1 minus 1 by E. So, what we have seen in this slide is we started with a Kelvin model, and when we applied the creep load, we got this as the strain response. And looking at the pictorial representation of this equation, we notice that the instantaneous strain response is 0, and when if we wait for long times, it reaches a constant value. Now, we will look at few other loading conditions where we cannot directly solve this equation, or even if you attempt to solve, the solutions become very tedious. But if we revoke the superposition, which is applicable for linear viscoelastic materials, solving these special loading cases becomes easy. So, we will be looking at superposition. So, first we will solve for creep recovery. So, we know for creep recovery the nature of the loading is, so we apply a constant stress and remove the stress at a instant. So, the constant stress applied is sigma naught and it is removed at time t naught. Okay. So, how do we apply this superposition, or in other words, how can we use the information which we already have been showing for a Kelvin model, and with creep loads we have already shown you the response. Can we use that information to solve this kind of input is the thing we will see here. So, in other words, can we write this creep recovery as sum of step functions? So, can we write this as a sum of two step functions? So, let us see how we can write that. First will be the normal creep load, saying that at time t equal to 0, we apply a load sigma naught, and that sigma naught is constant or remain present for the entire duration. But how do we bring in this information that at time t equal to 0 the load comes back to 0? For that, we apply another step load. This time, instead of applying a positive step load, we will apply a negative step load starting at time t naught. So, at time t naught we apply a negative. What should be the amplitude? The amplitude should be the same as the first one, so that both when we add them together nullifies. So, what I was saying is this value should be minus sigma naught. Okay. So, how do we write the expression for the first step function? The first step function is simply sigma naught times h of t, and for the second step function it is the same magnitude sigma naught with a negative sign, because now we need to help it to negate the first step function. And when does the unit or the step occurs? It occurs at time t naught. So, we write it as h of t minus t naught. So, the creep recovery load can be written as sigma of any time t is given as the first step function, which is the sigma naught of h of t, minus the second step function, which is the sigma naught of h of t minus t naught. This will be our input. So, individually we know the responses of each of these step functions. So, we can use that solution and superpose to get the response to the creep recovery. So, how can that be done? So, for the output strain we can go one at a time. So, what is the response for the creep load? We have seen it in the previous slide. So, this is the response we have seen for creep load. So, the creep load occurs at times less than t naught, but at times greater than t naught we have two creep responses. So, it will be the first creep response, which is again the same, for this we need to add the second creep response, where we simply replace t with t minus t naught. So, this occurs when your time is greater than t naught. So, now we are able to write the creep response as a sum of two step functions. Similarly, let us look at another example where we will be looking at realistic creep load. So, let us first look at how the ideal creep load looks like. we know that the ideal creep load is at time t equal to 0, there is a sudden increase in the load from 0 to this value of sigma naught, and then it remains constant. But now let us look at the reality. How do we conduct this test? We need to apply a load using a machine or a device, right. But is it really possible in reality to apply a load such that it goes from 0 to sigma naught? The answer is no. No matter what sophisticated machine you take, it can apply the load in a fraction of a second, but not at time t equal to 0. So, which means in reality, if one is conducting a creep test, this is how it looks like. You take a very short time, let us denote it with t naught. This t naught can be a very small value, let us say 0.1 of a second, but between that 0 and 0.1 second you are going from 0 to load sigma naught. And then after that time t naught, the stress value remains constant. So, what we said is this is an ideal scenario and this is the realistic scenario. Okay. Now, the question is, once we know that we are applying a realistic creep load, then how do we find the response? So, if we look carefully, again we should be able to apply or invoke the superposition to help us solve this problem. So, this can be written as sum of two unit functions again. The first part can be represented using a constant strain load or the constant stress load in this condition. This constant, let us say, is R. That R, of course, we know is sigma naught by T naught. But what we are saying is we are applying the constant stress load, let us say constant stress rate, and how do we ensure that at time t equals t naught the value becomes constant? For that, again we need to apply one more constant stress rate, but with a negative slope. But this should happen at what time? It should happen, it should start at time t equals t naught. So, at time t equals t naught, now we apply another load with the same slope, but in the negative direction. So, this is minus R, where R we have already defined as sigma naught by T naught. So, this is the same R. Now, let us see how do we write the equation in terms of functions. For the first step function, it can be written as stress R, stress sigma is R T times H of T. This Heaviside function ensures that the loading only starts from time t equal to 0 and less than time t equals 0, there is no load. And for the second step function, it is minus R, it starts at time t minus t naught. So, we replace t with t minus t naught and the Heaviside function should be written as t minus t naught. So, effectively the realistic creep load can be written as sigma equals the first step function R t times H of t minus R t minus t naught times H of t minus t naught. So, we have shown that this realistic load can be seen as a summation of two step functions which are both constant stress rates. So, once we are able to solve this problem of constant stress rate, once we can find out what is the strain because of the constant stress rate, we can use those solutions to find what is the strain for the realistic creep load. This I will leave it as an exercise so that you can work on using the methods we have been discussing in previous video and in this video. To summarize, in this video we have shown you the derivation of how the stress and strain are related in a Kelvin model. So, once we got that stress strain relation, we used it to find what is the creep response of the Kelvin model. We have not shown you the response for the relaxation, but I hope you remember that for a Kelvin model it is not possible to apply a relaxation load, because we have the damper in parallel, we cannot apply a instantaneous displacement. That is the reason why we have not been discussing about the relaxation load for the Kelvin model. But once we have the stress strain relation and we have also shown you the response under creep load, we showed you how can we invoke the superposition to solve some other loads such as the creep recovery and the realistic creep load shown here. So, until now we have only shown you the Kelvin and the Maxwell models, which are considered to be basic, but in order to model the real polymers we have to go beyond the Kelvin and the Maxwell models.